Okay, so recording in effect, and off we go. All right, so forces can be represented as vectors, and we can look at the resultant of two forces through vector addition. Equilibrium is something we're going to be talking about more today. And we did a couple of questions, notably one that looked like this, very simple question. We started off with this because this was a good way for us to introduce the concept of taking a vector and splitting it into its component parts. So a horizontal component and a vertical component. So the vertical component we said was your along your y-axis, and we used the sign to figure that out. So we take the vector and multiply it by the sign. That gives us a vertical component. We could figure out the horizontal component by using cosine. So I always said, think of cosine as your x, think of sine as your y. When you're trying to find those two components, breaking down the vector into those two components. Does it have to have two components? No. If a vector was going strictly to the right or to the left, it would only have one component. If a vector was going strictly up or down, it would only have one component. But many vectors have more than one component, which when you sum them gives us the actual vector itself. All right. So we looked at the same lawnmower question. It's just the calculations for it here. And then we sort of got more into how we find those components, which is what this page is about. And we used two different strategies to find the resultant of pulling on this common point with different forces and an angle between those forces. We did it using a regular parallelogram approach, which is what this page is about. And then, let's make sure I can monitor the chat as I go along. And then we said, okay, let's try another strategy. Let's do it by actually breaking down the vectors that we're using into components, right? So we can think of one vector as lying right on the x-axis, and that's convenient because then we can just simply write down the coordinates of that point as being the x-coordinate, which is equivalent to the force of that vector, and 0. Right? And then from there, we put our angles that take us to the other places. And then we said, okay, we get the same answer, obviously, because it's just another strategy to get to the same destination. And I said, it's a good idea that we have this other strategy because what if you're looking at adding, let's say, three vectors together? And it gets far more complicated to try to do this using the parallelogram approach. So if we just simply take the x and y components and add them all together and find using the distance formula, find the length of the resulting vector, then that would be probably a better way for us to tackle that. And here's the answer that we got in this case. We didn't actually finish getting the direction because this question only asked us for the magnitude of the resultant force, but we could have gotten that from using the tangent. We said this on the previous question because the tangent of the angle that we are going to have is going to be, which represents the direction of the vector, would be equal to the y over the x. So the y, the sum of the y's divided by the sum of the x's will give us that angle. We didn't actually do it in this case, but it's actually very doable. All right, now let's get to the new stuff. Very, very typical question, and I'm going to tell you right, this is what your homework is based on, and also on the assignment part of your test. Somebody had a question about the assignment earlier, which I don't think I answered. Let me see if I can just go back up and find that question. Hang on one second. It's just a problem set. So even though I'm not going to have a formal problem set per se, I mean, I think there's one in the MVL. We can't cover all of that ground. So I will let you know the questions that you should expect to see. So I'm answering Ashvan's question here. I'm going to let you know which questions you should expect to see on the assignment part of the test. And whether I'm going to make it 2 periods, I mean, I don't know if we can really spare 2 periods with the amount of time that we have left for in-class instruction or for class instruction. So we'll see whether I sort of condense it into a half a period for the test part and a half a period for the assignment part. I haven't made up my mind on that one yet. We'll see. But a question like the one we're looking at right now, Ashvan, will be on the assignment part, okay? And that's why it's important for you to follow along what we're doing here and then get the homework done to make sure that you do it for yourself and not just watch me do it. I've already made the analogy of a personal trainer with you. Watching a personal trainer doesn't make you get fit. It's when you actually start doing the exercise yourself. Same thing here. So I know you're going to watch me carefully. I'm assuming that's what you're doing as when you're here in class. But until you do this for yourself, you really don't realize whether you have fully grasped it or not. So I'm going to urge you to make sure you get your homework done on this one. Okay, so let's look at what the question is talking about. A 20-kilogram mass is suspended from a ceiling by two lengths of ropes that make angles of 60 degrees and 45 degrees with the ceiling. Determine the tension in each of the ropes. So there's a concept in what we're doing called static equilibrium. And let me write that phrase down. Static equilibrium, hold on. Static equilibrium, hope I can spell this right, basically means you're in a state where everything balances out. So for instance, if I'm hanging this 20-kilogram weight on this using these two pieces of rope, and the weight is not too heavy that it is going to pop the ropes and it's going to fall to the ground, it means that you're in a state of equilibrium, static equilibrium. The mass that you're suspending from these two ropes is going to be equal to the tension that you're creating in these two ropes. Hence, the weight is able to stay in place. That's basically what we mean by static equilibrium. So we're trying to decide, and if you are the engineer who has to put the ropes there to make sure that this thing doesn't fall to the ground, you need to understand, you need to figure out how much tension is going to be applied or to be, is going to be, applied, I guess is the best word, to each of these ropes so that it doesn't fall. All right. So one way to do this, and I'm going to do this both two ways. One way to do this, and by the way, it tells us that the angle that the two ropes make with the ceiling are 60 degrees and 45 degrees. All right, so that's what they're showing us here. And what I'm going to first of all say is that this mass has of 20 kilograms, and I said this to you. Let me go back to, I think it might have been the third page. Where was it? It was here. That tells you that the magnitude of the gravitational force is a product of the object's mass and its acceleration. So the acceleration due to gravity is 9.81. We'll just use 9.8 for most of our calculations when we're doing this. You simply multiply the weight of the object by the acceleration due to gravity, and that will give you the force which that object is actually exerting. So when we go back to this question, it means that this 20-kilogram weight, right, will, if we multiply it by 9.8, give us the force of newtons. And I don't have my calculator nearby. Could somebody just quickly work out 20 times 9.8 for me, please? 20 on your calculators. You have your calculators handy close by. Hopefully you do. Could you tell me what that is, please, on your calculator? 20 times 9, 196. Thank you. So what that is telling you is that, in fact, it's on the diagram right here, Mr. Kamak. Okay. What that is telling you is that the force that this thing is basically exerting on the two ropes is 196 newtons, right? So it means that when I look at the two ropes that are together holding this mass, it means that the sum of the force that these two are exerting must be equal to the force of the weight of this object. All right, let me say that again. Excuse me. The two things must be in balance. They must be equal for the weight to stay suspended there. So one way to do this, excuse me, is to create this vector diagram over here. And what you're in effect doing is you're leaving this 45 degree angle vector here, the one that's pointing up and to the right. You're leaving that right there, right? But then you're also putting, in a sense, you're taking this vector, the T1 vector, and sliding it down here, right? So in effect, you're putting the same vector here. Actually, I should use a line tool for that, shouldn't I? All right, so let me find the line tool. And let's erase this first of all. And you're taking this vector that you have up here, and you're in effect putting it down here. So now what you're saying is that if you went this way and then this way, it will be the same as actually going, and let me put a dotted line to represent the other motion. It will be the same as going from here to here. Right? And that's what this diagram over here is basically trying to tell you. That I'm adding the T1 vector and the T2 vector to create a vector which is running from the base of the T1 vector up to the tip of the T2 vector is really what we're saying. And that's because we slid that T1 vector down here so that the head of that vector is on the tail of the T2 vector is really what we're doing. Now, this diagram over here is basically trying to show you that. Now, it's not drawn to scale or anything, but that's what it's basically trying to show you. Now, notice a couple of things. The angle that we have up here, let me put another line here. That would be the same as the ceiling in the first diagram. There's a 45-degree angle here. If you look at the first diagram over here, there's a 45-degree angle on the outside here. And because this is a right angles to the vector that's pointing up, that must mean that this must be 45 inside here as well. And by the way, this vector that's pointing up must have a 196 Newton force to balance the vector that's pointing down to suspend this weight of 20 kilograms. So that's why this vector that's pointing up has a magnitude, right? The force of that vector is 196 newtons because this one, it's the exact opposite vector to the vector that's pointing down, right? Which keeps that thing in place. Okay, so there's a 45-degree angle here. Let me just point to it with my mouse. There's a 45-degree angle here, which means there must be a 45-degree angle on the inside here, which also means because of interior opposite angles that there's a 45-degree angle right here as well, right? 45 here must mean that there's a 45 here, right? 45, remember, you have two lines that are parallel, then we call them interior opposite angles, right? They are equal. So if it's 45 here, there's also 45 here because, and this is actually an isosceles triangle, by the way. This has to be 45 up here. Remember what I said, trigonometry is the basis of vector math. So you really have to remember all your stuff you learn in trigonometry. The other thing is that there's a 60-degree angle here. Remember, this vector with the horizontal was making a 60-degree angle right here. So with this horizontal line that I'm putting in, there's another 60-degree angle right here as well, which obviously means that because it's a triangle, there's a 30-degree angle down here. Okay? If I'm going too fast, you please let me know, you stop me. So it means that this angle that is in between, right, these two vectors must be 60 plus 45. So the 45 comes from this being the interior opposite angle down here, and the 60 comes from the angle that you make with the ceiling up here. So this is a 60 plus 45. It's always going to be, just so you know, it's always going to be the sum of these two angles here. The 60 here and the 45 here is always going to be what these two angles will be in a triangle that you create to form this vector diagram. All right, okay, where does the 9.8 in equation come from? Okay, so I was saying, Ariana, I took you back a few minutes ago, and I'll take you back again. Thanks for the question, by the way. Here we go. On this page, it says that the Earth's gravity causes objects to accelerate at 9.8 meters per second squared. The magnitude of the gravitational force mass times this acceleration. So the mass of the object is the 20 kilograms, and you multiply that by the 9. So that's always going to be the case. If you get a weight, all right, and you take that weight and multiply it by the acceleration due to gravity, and that gives you the force that it will exert. And the same goes for everything. So your weight, my weight, all of us are exerting a force downward right now onto the ground, and that's just simply by multiplying whatever your weight is by 9.8. All right, so thanks for the question. So let me go back to where we were. Okay, here we go. So this angle right here, let me say it again, is always going to be the sum of these two angles, the 60 and the 45. The other two angles will depend on what this angle is. So if this is 60, then this is going to be 30. And this is 45, but this has to be 45 because a triangle always has to add up to, as you know, 180. So what you should always check is when you've put your vector diagram together, as I've done here, check if all of your angles do in fact sum to 180. Now, remember, we're trying to find T1 and T2. That's our goal, right? What's the length of T1, which will equate to its Newton magnitude, right? Its force magnitude, right? We know that this vector here, this upward pointing vector, which is a sum of the T1 and the T2, that has a magnitude, a force magnitude of 196 newtons. Okay? All right. So how can I find T1? No, here's what we have: all of the angles in this triangle, right? We have this angle here, which is what, 105 degrees. That's 45, that's 30. So we have all the angles in the triangle. So if we have all angles, and again, I'm taking you back to your grade 10 trigonometry. I have all the angles and I have one side. This side here that I'm pointing to is my 196 side. Can anybody tell me what would be a convenient way for me to find my T1? Right? What am I going to use to find my T1? Remember, I have all the angles. All the angles are right there in the triangle, right? And the triangle I'm talking about, if I could label it, I'll call it ABC. So A, B, C. Can you tell me, and I'm trying to find the side going from, let's go from A to B. That's my T1, right? Can you give me a suggestion as to how I could find, based on trigonometry tools that you learn in grade 10, can you tell me how I can find the size of T1? Because the size of T1 is my force vector, and I need to know its magnitude. Okay, so can you tell me, please, anybody? What am I going to use? Sine law. Excellent, Richard. Excellent. All right. Some of the same people all the time. I really would like to get involvement from everybody. So remember what the sine law says. Sine law says that I'm trying to find a side. So I'm going to put the sides on top. That A over the sine of A is equal to B over the sine of B is equal to C over the sine of C, right? The small letters refer to the sides, and the big letters refer to, the uppercase letters refer to the angles. So what we're looking for now is an angle opposite to a side where we know both. So tell me now, not just Richard, right? Can't just be Richard and then a few other people who have always participated. I'm going to get my wheel out. Don't let me get my wheel out, folks. Which side and which angle do we know, right? Because we need that to be able to use a sine law. We can't use a sine law unless we have a side opposite to an angle. We know both the side and the angle. So can you tell me which pair we can use? Don't think about A, B, and C. Well, I guess you could think of it as A, B, and C, right? Except that, okay, you know what? Let me label these sides. Let's call this side here the side that's opposite to B. We're going to call this my side B. This is my side A. This is my side C. Remember that the uppercase letters refer to angles and my lowercase letters refer to sides. So I've gone ahead and I've labeled my triangle with the same letters A, B, and C. So what do we know right now that we can use to put into, and by the way, when you're using the sine law, right, and I don't expect to have to teach you sine law again, seriously. When you're using the sine law, we only use two at a time. So we don't need to use all three of these and set them equal to each other. So we can use the A and the B, or the B and the C, or the A and the C. We don't use all three at the same time. Just reminding me of that. So look at the diagram again, and you tell me which side do we know and which angle that's opposite to it that we also know, because we have to use that to figure out what our T1 is. We're going to focus on T1 first. Can anybody tell me what that is? Folks, I need, look, if I need that wheel, I'm going to get the wheel, but I really would like it to be voluntary. Side and angle. You tell me. I've labeled all the sides. We have labeled all the angles. What side do we know? So we know, let's see now. Sarah says we know A and B. We know A, actually we know A, B, and C. We actually have C as well, to be honest, right? But what I want, and so thanks for that observation, Sarah. But what I want to know also is which angle and which side do we know, right? Which ones are opposite to each other that we know? That's what I'm trying to get at here, because we need that to set up our sine law. Which side and which angle opposite to each other do we know both? We need to know both the side and the angle. Okay, so we know both side B, thank you very much, and we know angle B as well. That's exactly right. So we're going to go on that. We're going to set up our B, right, which is the 196, and put that over the sine of the angle opposite to the side B, and that would be the 105. And now, that's a 5. And now, which side represents T1? Which of those sides represents C1? All right, we're trying to figure out T1 here, folks. Which side is opposite to T? So small c, thank you very much. So set that equal to C, which we're going to call it C. We're going to leave it as C, over the sine of the angle that's across from C, opposite to C. And what angle would that be? Which is the angle that is opposite to C? It would be 45. Thank you very much, Kali and Ashfan. Could always depend on you. Over the sine of 45. Okay? So this is how we're going to find our T1. We're going to do exactly what we've just done. So if you remember, we're going to cross multiply. So C, and I'm going to be calling on one of you in a second. So I'm going to grab my wheel after this. It's going to be 196 times the sine of 45 divided by the sine of 105. All right? So let's see what we got here. I'm going to be asking you all to get your calculators out. Everybody, calculator. Make sure this is just something that we're all actively participating in. Alicia, you're up first. Alicia, check in for me, please. Let me start with doing that. Let me know you're there, Alicia. Great. Alicia, could you work that out for me, please, and tell us what that is? And I know it's going to be some decimals, so I'll just put approximately equal to on top there. Could you work that out for us, please? Tell us what that is. What is the C? In this case, it's the T1 that we're figuring out here. And I'm going to be asking somebody else for the setup for the T2 as well. And if you're paying attention to how we set up for T1, then you should be able to set up for T2, 143.48. Thank you very much. And I put N beside that because that's in newtons. And I'm assuming everybody else got the same thing because you all did this for yourself. Didn't just depend on Alicia. Thank you, Alicia, by the way. And can I get some agreement to that? Same, Cyrus says, okay. And Ashfan, of course, and Carly, yeah, some of the same people. Okay, good, excellent, excellent. Okay, thank you very much. Okay, so that was good work from Alicia. No, we need to set up to find, and that's my T1, by the way. So therefore, T1 has a force or sustains a force of 143.48 newtons. All right, so from Alicia to Fernando. All right, very close in first names, but this is Fernando we're talking this time. Fernando, please check in for me. Excellent. Okay, I need some help with setting up to find my T2. Let me take you back to the diagram. All right, how am I going to set up to find that T2? So what over what? Okay, remember, we always use the side and the angle that we know. So that would be a good starting point, right, Fernando? Right? We could use the same, could we use the same starting point that we just did a few minutes ago? Would you agree with that? Okay, so that starting point, I'll remind you, was 196 over the sine of 105. So I'm going to write that down. 196 over the sine of 105 is equal to. Now, change your perspective, please, Fernando. We scroll back up. And now we're trying to find T2. So what do I put over what to figure out what T2 is? Help me out with that, please. Right? I'm looking for T2. You can see my diagram, hopefully. So it's A over the sine of 30. Thank you very much. So A over the sine of 30. Therefore, A, and I'm going to be, thank you by the way, Fernando, I'm going to be asking somebody else for that in a minute, is equal to 196 sine 30 over the sine of 105. Okay, so please make sure you have your calculators handy. And I'm going to be asking this next person to do that calculation for us right now. That goes to Sarah. Sarah, can you please check out, first of all, check in for me, please? Let me know you're there. Perfect. Can I get you to calculate that? And then can I ask if everybody else, hopefully you all have your calculators out, are getting the same thing that Sarah's getting. So Sarah, please go ahead for me. 101.46 newtons. 101.5. I'm putting that down confidently, assuming that everybody else and Kushi is, look at that, Tom. Okay, perfect. So I'm going to go ahead and say that therefore T2 has a force of 101.46 newtons. All right. So remember, thank you, Adam, and thank you, Carly and Jordan and Tom Leo and Sarah and Kushi. Really appreciate all of you chiming in on that. So remember, I think the key to this thing is getting, let me take you back to the diagram again, right? Because getting the diagram in the first place is one big part of this. And again, I'm going to show you another way to do the same thing, right? And I think it would be good if you were able to do both ways. But let me get the diagram straight in your mind. 60 degrees and 45 degrees are two angles that the rope makes with the ceiling. If you slide the one of these, doesn't have to be this one. We could have easily have taken the T2 vector and slid that down here. But if you slide, let's say that 60 vector down, it's still pointing up and to the left, and connect to the end of the T2 vector, then the vector that you eventually get from summing those two vectors would have to be the same force as the vector that's pointing down to suspend the weight of 20 kilograms. The weight of 20 kilograms exerts a force of 196 newtons. So this line, this upward pointing line, must counterbalance these two other vectors. When I take this vector and add them together, I'm getting this vector, which represents the counterbalancing vector for the vector that's holding the weight in place. So what we did was we said, okay, that means that the angle that this 45-degree line makes with the ceiling must be the same as this angle on the interior opposite of the horizontal that you create below the original ceiling. So there's 45 there as well. The 60 degrees that you have up here will be the same as the 60 degrees down here, but therefore the same as the 60 degrees up here. So 60 degrees with the horizontal is the angle that this is making. So these two together combine to give me the angle that's formed at the intersection point between the T1 and the T2 vector. The other two angles should be easy enough to figure out, understanding that a triangle must sum to 180 degrees. So there you go. And our final answer, the T1 has a force of 143.48 and the T2 has a force of 101.46. Now notice that we need to add these two vectors together, and the sum of these two numbers, the 143 and the 101, should be sufficient to handle this 196. Actually looks a little low to me, but anyway, should be sufficient to, oh, no, I'm just remembering that it's 101. So the two together, when you add them up, is more than the 196, obviously. But the fact is that you lose a little bit of each of the force of the vectors because they're at an angle like that. The other thing you should probably notice is that the T1 vector, the one that has the the bigger angle tends to bear more of the mass. That's something that you might want to sort of bear in mind. Bears more of the weight of this object because the T1 vector, right, the one at 60 degrees, does in fact have a 143.48 tension in that particular rope. All right. Okay. Well, that's one way that you need to be able to do a question like that. Here comes method number 2. It's the same question. So I should get the same answer, right? But now we're going to tackle it in a different way. Now we have a T1, a T2, and a T3 vector. So I'm having 3 vectors in all. The T3 vector is still the vector that represents the force of the weight going down. So that T3 vector still, as it did before, has a 196 Newton force pushing down. Now, that force pushing down, so vertically downward, is exactly balanced by the component of the T2 vector, which is pushing up. So this component here, which we can call, I think I'll call it T2y, T2 comma bracket y. In other words, it's the y component. Remember, the vertical line is along the y-axis, is the vertical component of the T2 vector, which is the y. And the same thing over here. This vector over here, right, T1y, right, I'm calling it T1y. That's the vertical component of the T1 vector. The other thing is that this T1 and T2 vector also have horizontal components. So I'm going to call them T2x, and I'm going to call this T1, sorry, let me fix that. I'm going to call this T1x, right? So each of these vectors, the T1 and the T2, those can be broken into X and Y components, just as how when we had the lawnmower in the very first question, just as how when we had the people pulling the tug of war in one of the questions that we did already. When we have any vector, as long as it's not going strictly along the x-axis, strictly on the y-axis, it has two components, a vertical and a horizontal. So we're saying that the T2 and the T1 have both. Now, here's what we're also saying, that the T1 vector and the T2 vector in the x direction must balance each other out, right? The T1 vector plus the let me write this down. The T1 x vector must be equal to, or I'll put it a different way. Let's write it a different way. Let's say that if I were to subtract T1x minus T2x, that result should be 0. Why am I saying that? Because those two vectors are pulling in exactly opposite directions and must balance each other out. That's what we call the static equilibrium here. I know some of you are going to look at this and think this looks way harder than the one we did before. Okay, fine, but I still think you need to follow the steps involved in doing this. It's up to you as to whether this is how you're going to do this for yourself or not. I will let you decide that. But I think especially when you're doing a lot of, when you're putting a lot of forces together, breaking them down into their components makes a lot of sense. Okay, so the T1x and the T2x, when you subtract them from each other, you should get 0. The same thing is true if I add the T1y, right, and the T2y, add those together and subtract from that. Let's just put the 196. Okay, let's put the T3 then for now. We know what the T3 vector is already. That should also be equal to 0. Let me check in with the rule and make sure that I'm not sounding like I'm talking Greek here, right? So Kushi, how does that sound so far, right? Does that sound about like that makes sense? Can I go over that? Okay, Ariane, I sure can. And I like when you say, can I go over that? Because that tells me that you're really trying to follow. So let's go over that again. All right, so here's what we're saying. The vectors that we have, the components of the vector that are running along the x-axis must balance each. If this thing is standing still, it's not swaying back and forth, it's not pulling the thing so far down that it's popping the wires, right? That must mean that there you have static equilibrium. Nothing is moving. It's staying in place, right? We're not taking account of wind or anything like that. That would be another force that we could bring in, but we're not bringing that in. So we're just saying that it's in a still air where there are no other forces apart from the forces that we're talking about here. So there's a force in the x direction for T1 pulling left. there's a force in the x direction for T2 pulling right. Does that make sense so far, Ariana? Does that does that part make sense? Okay, good. So I'm saying those two forces are basically equal. Or another way of saying is that say T1x minus T2 is equal to 0, right? The two x's must be equal to 0 is what I'm saying, right? Also, if I add these two upward forces, the T1y and the T2y force, is the y part. Okay, so you have two upward forces here, which come from the wires, right? And one downward force coming from the weight. And I'm saying that those have to be equal as well. Does that sort of make sense? Right? If we have static equilibrium, if the x's are balancing each other out, then the y's are also balancing each other out. There are two y's. There's a y component that comes from one chord, and there's a y component that comes from the other chord, and those two are both pulling in the same direction, so we can add those two together. And there's another y component coming from the weight, which is pulling in the exact opposite direction, and that's the one that's 196. Okay, good. Okay, no. No, we could have written this differently, right? We could have put just the 196 here and then set it equal to 196. I mean, we can do that. We can do that later on. No, let's get back to something that we knew that we learned a couple yesterday, as a matter of fact. How do I get my T1x? Now, we don't know what T1 is, right? That's what we're trying to find. But we do know that the magnitude in the let's focus on the x's for now. The magnitude in the x direction, how do we get that again? How do we get that magnitude in the x direction? Can anybody remind me how to get the magnitude in the x direction, the T1x? This part of the function right here. How do I get this T1x here? Anybody remember how we get that? Come on, folks. In fact, we just went over that. We're going to use the cosine, and it's a cosine of the angle. So if we take the vector T1, right, and multiply that by the cosine of the angle, and remember now, by the way, I'll just remind you of this, that if this is 60 degrees inside of this triangle, then this angle that this makes with the horizontal down here is also 60 degrees. So it's going to be T1 times the cosine of 60. Can I just make sure? Whoa, 90 minus 60. Okay, let me just see what that's saying. No, Cushy. Let me just make sure that we're good with this. If this is 60 inside of this, okay, let me show you where 60 is. 60 is right here. Oh, I think what you're talking about is the angle. I know what you're talking about. The angle that makes up the right angle. But that's not what we should be doing, though. I'm looking at the triangle. I'm looking at this angle right here. That's the angle that I'm looking at. Does that make sense, Cushy? That's inside the triangle, with the little red dot, little red angle. Okay, good. And if that's the angle that we're looking at, then for us to find the horizontal distance, right, well, that's cosine, right, that's your y coordinate. It's going to be the T1, whatever T1 is, multiplied by the cosine of 60. Okay? And in fact, I'm going to set it equal to, rather than saying, well, let me go back to black, is equal to the T2 times the cosine of, well, let's look at what T2 is. Remember, it's 45 degrees up here. That means it must be 45 degrees inside here as well. So T2 cosine of 45, right? So we take the vector that we're trying to split apart and multiply it by the cosine of the angle that it's making with the horizontal. All right? Do I need to explain that again, or is everybody okay with that? Does that make sense? So T1 times the cosine of 60 is equal to T2 times the cosine of 45. How about Vanessa? Vanessa, is that making sense to you as well? Just checking with you. Okay, thank you. Shashti still calling on for Shashti. All right, no Shashti. All right, so here's one thing we can do now is you can isolate either the T1 or the T2. I'm going to go with T1. So I'm going to say that T1 is equal to T2 times the cosine of 45 over the cosine of 60. You'll see why I'm isolating it in a minute. Okay, just bear with me on that. Bear with me on that. So T1, I'm just isolating T1, is equal to T2 times the cosine of 45 over the cosine of 60. All right? Okay, let's get to the second. And we can't solve for T1 and T2 with just one equation. That's not enough. So we need more information. Let's go back to the y values now. We said that our T1y plus our T2y must be basically equal to this 196 force. So how do we get our T1y? Well, we know this already. So T1y, well, you tell me. Come on, folks. Let me come back to the room here. How do I get my T1y? So I'm trying to fill in for this information here. How do I get my T1y now? Right? Let's see. Tomalea, can you help me out with that, please? How do I get my... Okay, Richard jumped in. All right, that's good. You're going to use sine. So we're going to say that my T1 times the sine of T1 was 60 times the sine of 60 plus my T2 times the sine of, I guess it must be 45, is basically equal to 196, is what we're saying, right? Right? When this is what this line that I'm pointing to is basically saying. So this line right here is saying if I take my T1y's and my T2y's, add those two together, those are the ones that are pointing up, and then I minus my 196 from that, because that's the force pointing down, then that should get me 0, or just simply set it equal to 196. That seems to, that should be good enough. All right. That's all right, Richard. All right. So, Shashti, still calling out for Shashti. Shashti, where are you? Have you come back to class yet? Right? I need to hear from you, Shashti. Where's Shashti? Still no Shashti. Let's keep going. So, guess what, folks? We now have two equations, right? One equation with T1 and T2 says that T1 is equal to T2 cosine 45 over the cosine of 60. Second equation says that T1 times the sine of 60 plus T2 times the sine of 45 is equal to 196. Okay. Can somebody suggest how we might be able to figure stuff out at this point? Where do you think I'm going to go next with this? What do you think would be a good strategy for us to solve for either T1 or T? I'm going to throw it out to the whole class. I'm not calling anybody in particular yet. What would be a good way for us to get either T1 or T2? Because we now have two equations, right? One equation, perhaps a substitution. Absolutely. Thank you, Kushi, and thank you, Taj. So I'm going to do exactly that. I'm going to make a substitution right now. I'm leaving things as sine of 60, sine of 45. I don't want to really disturb that yet. We'll deal with all of that later on. Say that my T1 is going to be replaced by T2 cosine of 45 times the sine of 60. Yeah. Over the cosine of 60. I think I left that out before. Plus T2 sine of 45. Yeah, pretty sure we left that out. Is equal to 196. All right. Yes, we didn't. Yes, Richard, you're right. We didn't multiply by the sine of 60 as well. I'm going to come back to just simply using the numbers. So anyway, so T2 was T2 times all of this is what T1 is. So I'm going to replace T1 with the T2 cosine of 45 times the sine of 60 over the cosine of 60. And then we can put that together now. So my T2 cosine 45 times the sine 60 over the cosine of 60 plus the sine of 45 is equal to 196. So we'll try this again. So T2 should be equal to the 196 over, yeah, we left a part of this out. Cosine 45 sine 60 over cosine 60. And sometimes it might be easier to work with numbers rather than keeping things in this form like that, plus the sine of 45. Actually, we don't need those brackets on the end. Okay, let's try that again, folks. I think it was Ariana who helped us out the last time. Ariana, that was you. Let's try that. Let's put that into the calculator this time and see how this works out. Okay, so we left out that sine of 60. Yeah. Folks, what are we getting when you do that this time? And remember that we should be getting 101.46, and that's what I got when I did it on my calculator. Ariana, what did you get on yours? You're still with us, Ariana, right? Just checking. Okay, great. And Richard, you were right. We did multiply by the sine of 60. We left that out. 101.46. Great. So that means that T2, and that's newtons as well. And by the way, to get our T1, right, we can just simply come back up here and say that T1 is equal to the T2, which is the 101.46, multiplied by, and I'm going to ask one of you to do this in a minute, cosine of 45 over cosine of 60. Cosine of 45 over cosine of 60. Okay, great. All right, that was Ariana. Thank you, Ariana. We didn't do the best job with that one, but we still got the answer in the end. And then I'm going to ask, let's see now, Kushi. Kushi, can you help us out to calculate that last part now, please? And I'll just reveal that for you so you can see it. Could you work this out for us for T1? So that answer, 143.49, I'm hearing. Now let's compare those answers to the answers that we had before. 143, well, 0.48, so close enough, and 101.46. All right, folks, so sorry about the mix-up. Here's the part that we kind of left out. There was a sine 60 that was part of this that we didn't multiply when we did this the first time. So it should have been the T2 times the cosine of 45 times the sine of 60 over the cosine of 60. So that was left out, and that's what messed us up the first time we did this. Anyway, so there's our T2, there's our T1. Again, those are both approximate. All right, I'm with all of that confusion, I'm so sorry about that. Is everybody able to follow what we did that time around? Maybe using the actual numbers rather than leaving it in exact form the way I did it might have been more useful. So something to consider when you're doing this on your own. All right, I'm going to move along. We have about 5 minutes left before this class is done. So let's tackle this. All right. And by the way, is Shashti with us now? Shashti, we were looking for you earlier on. Are you with us now? That was about, yeah, you got to stay with us, Shashti. Was checking for you about maybe 15 minutes ago, couldn't find you. So make sure you stay attentive in class, all right? Now, is it possible for three forces? So again, think about the static equilibrium that we've been talking about. Is it possible for three forces of 3 newtons, 5 newtons, and 9 newtons to keep a system in a state of equilibrium? In other words, can I fit these three sides together? You remember when we were doing the question just before this, right? In fact, I'll take you back to this one here. These three sides here are in a state of equilibrium. So the one that's going up and to the left, the one that's going up and to the right, balances out this one which is going straight up. So if you just sort of follow from here to here, from here to here, then that balances out this one that's going straight up here. So the question now is, can these three sides, so one side is 3, one side is 5, and one side is 9. These are three different forces. Could I put these into a state of equilibrium? What do you think, folks? A 3, 5, and a 9. And I'll tell you what the key to this is. Can I create a triangle out of these three sides? Is that even possible? Can I create a triangle? And I'll just show you. I measured these using the on-screen ruler. So this one is the side that's about 3, well, 3 centimeters, but 3 newtons for our purposes. This one is the one that's about 5, and this one is the one that's about 9, right? Approximately 9. So can I create a triangle out of those three sides? Is there a way that I can tell before I actually try to put them together whether they can create a triangle? Excuse me. Does anyone know when you can create a triangle from three sides? Is there some rule about whether you can or cannot from three sides? Well, I'll tell you what the rule is. The rule is if you can add any two of the sides, right, those two sides must be greater than the third side. Any two sides that you add must be greater than the third side. So if I add this 9 and this 5, that must be greater than the other side, which is 3. Well, it does check out if I did that. The 9 and the 5 add up to more than 3. If I were to add the 9 and the 3, which is 12, that's more than the 5. So again, that checks out. But if you add the 5 and the 3 together, that's not more than 9. There is no way for you to create a triangle, excuse me, from these three sides because it just isn't enough. This side is too long. If I put these here, if I just put these on top of this here, I think you can see more clearly that if I were to start arching these sides or rotating these sides up, this one up, that one up, it's right away, it can't even form a triangle because of the fact that they're too short. So these two sides together are too short to even create a third side from this. So these two sides have to be at least more than the third side. In this case, it is not. So the answer to this question is no, it is not. They cannot create a state of equilibrium because two of the sides are too short to be more than the third side. It works for 9 and 3. It works for 9 and 5. It doesn't work for 3 and 5. And all three conditions have to be met for you to be able to form a state of equilibrium, right? For you to be able to form a triangle, because two of the sides have to add to give you the third side, and that will not work in this case. So the answer to this question is no. Okay? Now, since it's 11:14, I'm going to hold off on doing this last example with you. 3, 5, and 7. No, this one does, right? This one is in a state of equilibrium because 3 plus 5 is more than 8. 3 plus 10, 3 plus 7 is more than 5, and 5 plus 7 is more than 3. So this one can create an equilibrium, and we're going to figure out the angle between the two smaller forces when we're done with the break, but we'll come back and get that done afterwards. In this question, no, this is different from the one before because the one before was asking whether they were in a state of equilibrium. And I pointed out that this one is not in a state of equilibrium because it doesn't pass the test of any two sides must be more than the third. The 3 and the 5 together are less than the 9. So that means it fails the test of being able to keep a state of equilibrium. If you had these three forces together, they wouldn't be static. They'd be moving in some direction, right? So that's why this doesn't pass the equilibrium test. Now these forces are meant to pass the equilibrium test. So 3, 5, and 7. So I'm going to represent them by some lines right now, right? So let's say that this is my 3. This is not going to be drawn to scale, so don't give me a hard time for that. Let's say that's the 5, and let's say this is the 7 right here, right? And they're in equilibrium, which means, and let me just specify, in fact, I should have used, I'm going to erase these because I really should be using a directional lines, right? Vector lines. I'm going to delete those. I want to put in lines that are directional, right? So let's say there is that. And then let's say there is this. Then let's say there's one that goes this way. Right? So those are the three lines that we're going to call our vectors which are in a state of equilibrium. Meaning, here's what it basically means. that this one takes you here, this one takes you, this one takes you back. So they all balance each other out. That's basically what it means. So what I'm going to do is I'm going to put some numbers beside them to represent their magnitudes. I'm calling that the 3, I'm calling that 5, and I'm calling this the 7. Not drawn to scale. Let's just be clear on that. What is the angle between the two smaller forces? Well, we could say it's this angle right here. We could say that, but it's not really that angle, right? That's the two smaller forces. The truth is that the angle between those two smaller forces should be measured when those vectors are tail to tail. So it would mean that this vector needs to be up here for it to be the two smaller forces end to end, right? So the two tails are together. But we can actually use the original, like in this condition, to figure out this angle between the 3 and the 5, and then use a supplement of that to figure out when they are tail to tail, because that's how you measure. It says angle between two smaller forces. The two smaller forces would be when the vectors look like this, right? Tail to tail. This is the 3, this is the 5. I move that up there. So angle between them with this angle right here. But for our purposes, to make it easier for us, we're going to actually get the angle if they had been not tail to tail, but head to tail. So does anybody know how we can get that angle that I just marked off, right? We'll call this angle here theta. Oh, sorry. We'll call this angle here theta. Can anybody help me to figure out how I could cosine rule? Well done. Well done, Richard. It's a cosine law. So let's set this up for the I'm going to remind you about the cosine law because this comes up in your homework, one of your homework questions. I'm trying to find that angle theta there. Let me put some letters on here for you. Let's call this, I'll call the angle that we're trying to find actually theta. So that's A, this is B, this is C. So again, small a is here, small b is here, and small c is here. Let me show you what the cosine law would be set up for you to be able to get that. It's going to say that the cosine of angle A is equal to the two sides that are around A. So what I mean by that is and I'll mark them off in red, I'll circle them in red anyway, the B and the C vector minus the A, not vector, well, vector really, minus the A vector. So I'm going to say that would be B squared plus C squared minus A squared all over 2 times B times C. That is how we're going to figure this out using the cosine law. So the two sides that are around the angle that we're trying to find, the two sides around the angle we're trying to find are the B and the C side. The side that is opposite to that is the A side, and that's what I'm going to subtract. And then on the bottom, it's 2 times B times C. If you have a test, I will give you all of these equations. You don't have to memorize. You just need to know how to use them. So in our case, that's equal to 3 squared plus 5 squared minus 7 squared all over 2 times 3 times 5. Okay? So that, and this is all what the cosine of A is. Let me see if I can do some of this mentally now. So that's 9 plus 25 minus 49 over, this looks like 30. Okay? So I'm doing a lot of this mentally, so I might make some mistakes here. 9 plus 25 would be 34. 34 from that would be 15 minus 15 over 30. Did I do that right? Which is equal to minus a half. Folks, help me out. I got that right? Okay, thank you. That's all mental stuff, folks. All mental. So the cosine of A is cosine of A is equal to minus a half, first of all. So of course, to get the A itself, it will be cosine to the minus 1 of, and I don't generally like to put minus a half in my calculator for when I'm doing an inverse function. In this case, I'm just going to go ahead and do it, right? because I do know what this angle is. This angle works out to be, I believe it's 120. You can double check that for me on your calculators. I would have normally, if I'm doing this, and I did this when I was solving equations in my advanced functions class, is put the positive in and then ask what quadrant you're in and all that good stuff, but I'm just going to go ahead and put it in. So I get 120. Now remember that that 120 is the angle inside of the triangle, but I pointed out to you before that I should be looking for, when I'm measuring angle between two vectors, the vectors have to be tail to tail. So I'm really looking for this angle out here, right? And that would be the supplement of the 120. So the angle that I'm actually looking for, so the angle between the vectors, right, tail to tail, would be equal to 180 minus 120, or 60 degrees. Okay, just want to make sure everybody's clear on that. That's what the answer needs to be. You have to make sure that anytime you're asked for an angle between two vectors, those vectors must be tail to tail. They weren't when we put it into the triangle, so we just had to figure it out inside the triangle and then take the supplement of that to get what the actual angle is. Okay, now let me just introduce you to a question that is going to be on your assignment. I'm always going to change up the numbers, but I'm just going to walk you through it now. If we have time at the end, we'll come back and look at it. But there's a lot of other stuff that I want to get through today, and I don't want to run out of time like I did yesterday. So this question requires two answers, magnitude and direction. Give the magnitude as for question one and for question two. So I'll tell you what I mean by question one and question two in a second. Powerful tug-of-war team capable of pulling with a force of 500 west challenged two other teams that tried to combine their efforts in a configuration like the diagram below. So this is the first team, and they pull with one team, right? They're mighty enough to pull with a force of 500 newtons going west. So west, of course, is to the left. Everybody should know that. And the two other teams that are going to try to compete against them, Team B and Team C. Team B pulls with a force of 275 going northeast, and Team C pulls with a 300 going southeast, south 85 east. And we can go over what that means. I did talk about that when we started looking at vectors earlier on. That's really 85 degrees east of south is what this is. And we can hopefully come back and look at this if we have some time at the end of the class. So the question is, determine the final force and direction of the sum of the vectors. So magnitude without units correct to one decimal place. We will put units on it of newtons. I just copied this from a question I gave to another class at another time. So that's why some of it might not sound as if I've really edited it for your class, but I will. Anyway, so the question is, what is the final force that comes from one force going to the west of 500 newtons and two forces combining, one going northeast and one going southeast? When you combine those, one is 300 newtons, one is 275 newtons, right? What would the resultant force be? And then who wins? And who wins is going to be determined by, obviously, the direction. Is it going to be pulled generally into the left or just generally pulled to the right? That's something that we should be able to determine using vectors. So start thinking about how we would solve something like that. This is going to be on your assignment. But we're going to come back to that at the end. We're not going to do that right now because I want to get to some other stuff today. Here's my success criteria. And I'm going to leave you to, pause the video later on when you are looking at the video if you want to see what the success criteria are. I want to get to the new stuff today. And that's looking at something called the dot product. So we're moving on, folks. We're moving on. New stuff. Right? What I did before was just finishing up stuff we had yesterday. And we'll get into some new stuff. But to understand the definition of a dot product, I want to get through both dot products and cross products with you before the end of this week. So today I'm going to tackle dot products. What's the definition of the dot product of geometric vectors? We're going to recognize that perpendicular vectors have a dot product of 0. We're going to recognize the properties of dot products, and we're going to be able to use dot products to find an angle between geometric vectors. So that's kind of where we need to go today. So let's start off with the definition of the dot or scalar product. And it's called a scalar product, and I'll tell you why. Because when you take two vectors and you find their dot product, you don't end up with another vector, as opposed to when you're doing a cross product. Tomorrow, when we start looking at cross products, that's my plan to get to cross products tomorrow. When you multiply two vectors together in a cross product, you end up with another vector. But when you take two vectors and get their dot product, you just get a number, a scalar. It's very simple to calculate, by the way. You'll see how simple that is in a minute. But looking at this diagram right here, if I had vector A and vector B, right, or vector AC, I should say, and vector AB, then it turns out that their dot product, and this is the first thing that I want you to pay attention to. The dot product of these two vectors, we'll get to how we actually compute them in a second, is exactly equal to the magnitude of the two vectors, so how long this vector is and how long this vector is, multiplied by the cosine of the angle between those two vectors. Again, on a test or on an assignment, you'll have the formula. You don't need to memorize it, you need to know how to use it, right? And this works for vectors that are between 0 and 180 degrees apart, right? So that's the limitation on the dot product between 0 and 180. However, the sign of the dot product is very useful for you to figure out something about those vectors. If vector A and B, excuse me, if vector A and B are, when you take their dot product, right? If the angle that you're using for the cosine is between 0 and 90, which is an acute angle, then what's going to happen is that your cosine is going to be positive, and that means that your dot product will also be positive because you're multiplying two distances, magnitudes, times that cosine, and therefore the answer is going to be positive. So as long as the angle is acute between 0 and 90, then your dot product will be positive. If the angle is exactly equal to 90, then your dot product is going to be 0. And why is that? Because the cosine of 90 is 0. Right? So 0 times anything gives you 0. If your angle between the two vectors is an obtuse angle, so between 90 and 180, which is when cosine becomes negative, then your dot product will also be negative. Okay? All right. So those are the signs of the dot product. And here's how we calculate dot product if we have the magnitudes of the vectors. Just take the magnitudes and multiply it by the angle, the cosine of the angle in between them. And that can be anywhere between 0 and 180. Okay. Properties of dot products. They are commutative. So taking A times B will be equal to B times A. The order is just like any other multiplication. Right? Doesn't work for when you cross products. Cross products are different, but for dot products, multiplying them in a different order doesn't change the result. You get the same result. The other property that's good for you to know is the magnitude property. If I take a vector and dot it with itself, then what you're going to end up, remember, you're going to end up with a number. Every time you do a vector across a dot product, you end up with a number. That number is going to be the magnitude of the vector squared, right? That's really what you're going to get because it's really, and let me tell you why that is. What would be, and hopefully this is going to be obvious. Let me take you back to the definition of the dot product again. It's the magnitude of the two vectors multiplied by the cosine of the angle in between them. Well, what if those two vectors were basically the same vector? What's the angle between two vectors that are exactly the same? What's that angle between? If I put two vectors that are the same together, what's the angle between those two vectors? Now I'm throwing it out to the class. It'll be 0. Thank you, Adam. So the cosine of 0 is 1. So what I'm going to end up with is just the length of A times the length of A, which means that is the length of A squared. That's really why this is what it is. Okay, associative property with scalars. Now, if I took a vector and multiplied it by a scalar, then multiplied it by another vector in a dot product, then I would get the same answer as multiplying that scalar by the second vector and then multiplying by the first. Or if I multiply the two together in a dot product and then multiply the final result by the scalar, they will all three of them be the same. Distributive property, if I have, and just like with regular algebra, if I have two vectors being added together, you know to add vectors already, just add the components. If I dot that with A, then I could actually get that by multiplying the A in a dot product with the B and then adding that to the dot product of the A and the C. So the distributive product holds for this. But here is another important property of dot products that I kind of want to stress now. If the dot product is zero, where neither vector themselves are zero. So in other words, this is not the zero vector. The u vector and the v vector are not the zero vector. We know what the zero vector is, a vector that has no magnitude. It's nothing. Then it means that the two vectors u and v must be at right angles to each other, right? That's an important property of the dot product. And we said that on the first page over here, right? We said that if the angle was 90, then the dot product would be equal to 0. So it's basically saying the same thing here, right? If u times v is 0, that's proof positive that the two vectors are at right angles to each other. Conversely, if the two vectors are at right angles to each other, so the opposite is also true, then it means that the u times v is going to be equal to 0. So u times v is 0, they're at right angles to each other. If they're at right angles to each other, then their dot product is going to be 0, right? This word is a word that I want you to get to know because you may see that in a question. Two vectors are orthogonal if they're perpendicular. So that's what orthogonal means. So perpendicularity and being orthogonal mean one and the same thing, right? And again, if the dot product is 0, they're orthogonal. Or if they're orthogonal, the dot product is 0. So those are some properties of dot products that are good for you to bear in mind. Okay, let's actually work out some dot products now. First one, find the dot product u and v, given that u is 8, that's the magnitude, and v is 3, and angle between u and v is in one case 40 degrees, which is in degrees, obviously, and the other case, root 3 pi over 4. Easy. Just go back and use a formula, right? Here's a formula right here on the first page. Magnitudes multiplied by the cosine of the angle between them. It's really that easy, right? So in this case, for A, it's going to be equal to, so this is going to be u, vector u dotted with vector v is going to be equal to the magnitude of 8 times the magnitude of u times the magnitude of v times the cosine in the first place of 40 degrees. Okay? As easy as that. Literally as easy as that. Last time was cushy. I'm going to ask the following person to get the calculator out and tell us what this answer is. Very simple to just plug into the calculator. Jessica, this is your question. Jessica, just check in for me first, please. Are you there, Jessica? Perfect. Could you please work that out for us? Tell us what the dot product of u and v are, or is rather, when the angle between them is 40 degrees. And I'm saying it's just simply multiplying those three things together. Go ahead, please, Jessica. And you can give it to me to, I don't know, maybe 2 decimal places. I know it's not going to be exact because cosine of 40 is not even a special angle or anything. $18.39. No, there are no units there. Thank you, Jessica, by the way. There are no units there. It's just a number. It's a scalar, right? It's not a vector. So vector dotted with vector, let me just say this again, gives you a number, a scalar. When we do tomorrow, vector crossed with vector gives you another vector. But just want to be clear on that. Now let's get, thank you, by the way, Jessica. Let's get to B. So I'm going to use the U and V again. But this time, the 8 times the 3 is going to be by the cosine of 3 pi over 4, right? Which I believe is an obtuse angle. Now, in this case, we can probably get an exact answer, I think. 8 times 3 times cosine of 3 pi over 4. And nobody put any answer in the thing here, please. Jessica, thank you very much. Let me take you out for now. Give me an answer for that, please. And by the way, your calculator now needs to be in radian mode. So Danny, first of all, check in for me, please. Let me know you're there. Earth to Danny. Where is Danny? Good. Danny, could you work that out for me, please? But make sure your calculator is in radians. Hopefully, you remember how to switch your calculator from degrees to radians. Okay? And everybody else could be doing the same thing, switching over first of all to radian mode and then getting an answer. And then you can compare that against what Danny is about to give us. Minus 5.9, I'm hearing. Okay, how does that compare with everybody else? Is that about right to you? Minus 5.9, is that correct? Something tells me it might not be. I'm just looking at, oh, cosine, never mind, I think it might be. Got mine, oh, that's a pretty different answer. That's a very different answer. Okay, so Danny's about to change now. Danny has a change of heart. Now he's saying minus 16.97. Okay, so I'm going to erase this then, Danny. Now I do know that this one could have been given in exact form because 8 times 3 is what, 24? And this is minus 1 over root 2. I do know that. So this should be the same as minus 24 over root 2, right? Whatever that is. You had that as well, Taj says. Okay, great. So it should be the same as that. But anyway, we're going to move on. Now, let's evaluate each of these dot products. Take you back to I hat and j hat. What would I hat times I hat be? Can anybody tell me what that might be? I hat times I hat. What do you think that should be? I told you before about what these are. Remember, these are the basis vectors, right? So you're saying it should be 1 squared. Well, you're right, because remember, the magnitude of I is 1. So it's a unit vector, right? So really what you should be doing is taking the I of 1 and squaring it, because the angle between them, of course, would be 0. And the cosine of 0 is 1. So it should just be 1 squared, which of course is 1. Okay? Is everybody clear on that? All right, the magnitude. Yes, thank you. Thank you, Sarah. It's the magnitude of the vector. Okay. So how about the I and the j? Right, so the first answer is this answer right here. I times I squared. Hold on. Which would be 1 squared. How about the I times the j? Remember, the I vector and the j vector are the basis vectors. What should the I times the j be equal to? What should I get from multiplying those two vectors? We've kind of talked about this. You know what the I vector and the j vector. Taj, why are you saying 0? Why would you think it's 0? By the way, you're right. Why is it 0 though? They're perpendicular. Of course they are. Right? Let me remind you that the I vector and the j vector, the I vector is a vector that runs from here to here up to 1. And the j vector is the one that runs from here to here up to 1. Right? So this is, if these two vectors are running along the x-axis and the y-axis, then they must be perpendicular to each other. Right? The angle between them is 90 degrees. right? And the two vectors, the scalars, sorry, not the scalars, the vectors will be 1 times the cosine of 90. Cosine of 90 is 0, so the actual answer will be 0. All right, remember, perpendicular vectors have a 0 dot product. So Taj is right. Absolutely right. No. If you were given a vector A, so A has these components, an x component and a y component, and given a vector B has an x component and a y component, then the dot product, so if we're given to you in terms of components, then the dot product is actually equal to, it's easier than you think, taking the A and multiplying it by the B. So multiply the two x coordinates together, multiply the two y coordinates together, and then simply add it up. It's really that simple. This property also extends to three-dimensional vectors. So if the A vector had three components, x, y, and z, and the other vector B had three components, x, y, and z, then to get the dot product, the A times the B, the two x's get multiplied, the two y's get multiplied, and the two z's get multiplied, and you just add it all together. So let me do the first one for you then. Then I'm going to ask all of you to do the second one and tell me what you're going to ask one of you to tell me what that is. So the first one is the dot product. So now we're giving it to you with these geometric vectors, 2 minus 1 and the 4, 3. Those are my two vectors. And by the way, I'm going to remind you, these are position vectors, right? I'm going to remind you what a position vector is. A position vector is a vector that, let me see now, 2 minus 1 would be a vector somewhere about here, right? Where the end of the vector, the head of the vector is at 2 minus 1. So I'm going to dot that vector with the 4, 3 vector. So let's say the 4, 3 vector is somewhere around here. So I'm trying to dot those two vectors together. In a little while, we're going to talk about how we can use this to find the angle between those two vectors. We're going to get to that. We're going to get to that. But I want to dot them. So dotting them is as easy as follows. I'm going to take the 2 and multiply it by the 4. I'm going to add that to the minus 1 times the 3. How easy is that? So the two x's get multiplied together, the 2 times the 4. The two y's get multiplied together, the minus 1 times the 3. And then we just simply add the result together. So that would be equal to 8 minus 3, which is equal to 5. It's really that simple, right? That is your dot product. Your dot product is multiplying your two x's, adding that to the product of the two y's, and that's it. You just add the two together. We're going to talk about negative reciprocals in a minute, something you learned back in grade 9, and why negative reciprocals give you position vectors which are perpendicular to each other. We're going to get to that in just a minute. So here's your task now. I need you all to work out what the dot product is between A and B. All right, everybody, work that out for me, please. I'm going to be calling on one of you for that answer in a few minutes. So Danny, taking you out for now. And I'm spinning the wheel in the meantime. And if anybody isn't clear on how to do that, based on what I just did for the first one, then you got to tell me no. And I have a name already for who I'm going to be calling on. Right? I'm asking you all now to get the dot product between A and B. Right? So here's A. I did the first one, A. Here's my A, here's my B. Find the dot product between those two, please. All right? Off you go, folks. I'm going to give you a minute to get that done, and you don't even need a minute because it's really a fairly straightforward operation. Is there anybody who isn't clear on how to get that dot product? Because you need to tell me no before I call on somebody and you're going to tell me you didn't understand what to do. Is there anybody who isn't clear on how to get the dot product? Got to step up if that's the case. Okay. Okay, so you don't really need a minute for that. Kashaf, first of all, check in for me, please. Let me know you're there. Perfect. Kashaf, what's the dot product for the second one, for B? What do you get for the dot product for that? Looking for the dot product, Kashaf, between those two vectors. So now we're in three space, but the three space works just like the two space. Okay, Kashaf is saying 22. I'm going to write that down. No comment yet. What do other people think? Is Kashaf right on the money there? Absolutely. It's as easy as that. You're going to take 1 times minus 2, 0 times 5, and 8 times 3, and there's your dot product right there. As easy as that. And you all thought vectors was so tough. Okay, no. Find the angle between each of the following pairs of vectors. Uh-oh. Find the angle. Okay, well, let's just think about this a little bit, right? We said that the dot product, let's just take the u and the v. If I took the dot product of the u and the v, that would be equal to the magnitude of the u times the magnitude of the v times the cosine of the angle between them. I'll just use theta for that. So can we not, and by the way, thanks Jordan and Sarah and Tash and Ashwan and Tomaleo for checking in on that, and Kushi. Oh, look at that. That's what I like. I like to see all of that participation there. That's great. Still not here for everybody, but anyway. So do we have enough information for us to find the angle between these two vectors? Turns out we do. In fact, if we took this formula for dot product, that u times v, dotted that is equal to the length of u times the length of v times the cosine of theta. And if we solve for the cosine of theta, then the cosine of theta should be equal to the u dot v. Again, these are both vectors divided by the magnitude of the u vector times the magnitude of the v vector. We know how to get the dot product. We just learned that. We know how to get the magnitude of a vector if we have the components of the vector. We should be able to do this. So the cosine of theta is equal to whatever this works out to be. Okay, so let's first of all go ahead for the first one and find that dot product. All right, so let me go back to my wheel here. Thank you, Kashaf, by the way. And I'm going to be asking you for the dot product between the two. So we're talking now about A. We're going to focus on A. Right? And this goes to Sarah. Sarah, first of all, just check in for me, please. Let me know you're there. I know you're there, Sarah. So just check in for me, please. Perfect. Can you tell us what the top part of this is? What is that dot product between what I just underlined there? What is the dot product of vector u and vector v? What's that dot product? Do exactly what you just saw. I think it was, remind myself who did that one a few minutes ago. Kashaf. Look at what Kashaf just did. So you're saying it's 10. Let me see if I agree with you. So that's 6 plus 4. Yeah, I agree with you. That is 10. Okay. So 2 times 3 plus minus 4 times minus 1. So that's 6 plus 4, which is 10. No, magnitudes. Uh-oh. Do you remember how to do that? All right, let me throw that out to the class. Before I sort of call on somebody, does anybody remember how we find the magnitude of vector u? Use a distance formula, absolutely. And in this case, good, Cushy, great, great. And in this case, what is the magnitude of the u vector, right? How would I find the magnitude of that u vector, right? Do you remember? So use a distance formula, good, right? So how long is that 2 minus 1 vector, right? Does anybody remember what that is? Cushy says root of 5. You're absolutely correct. You're absolutely correct. We take the 2 and square, take the minus 1 and square, add them together, and take the square root of that, it's the square root of 5. Well done, Kushi. Right? And then, what about the vector v? What is the magnitude of that vector? It's 5. It's 5. For vector v, it is just 5. Yeah, I see what you're saying. Square root of 25. Yeah, right. Yeah, you're absolutely right about that. Square root of 25. Yeah, couldn't agree with you more. Yeah. Okay, So I just put s squared at 25, which is 5. So now the cosine of theta, so the angle between these two, so now we know how to find the angle between two vectors. If we have the components of the vector, then all we have to do is to apply this formula of the dot product divided by the magnitude of the vectors, and we can find the angle between two vectors. Okay, so it's time for me to reach out to somebody to do this now. So remember now that to me to get the theta, it's going to be cosine to the minus 1 of the 10 over, let's put 5 root 5 then. All right, I guess that makes sense because we already know that the square root of 25 is in fact 5. So let me take out Sarah and let me reach out to, it's now for, is it going to be, yes, it's Shashti's turn. Shashti, hopefully you're with us this time. Shashti, please make sure you're with us now. Shashti, check in for me, please. Oh, come on, not this again. Shashti, where is Shashti? Shashti, where are you? It's the second time today, really. Shashti, I need to hear from you. All right, we're going to come back to you. We're going to have to find out why it is that when we call on you, we can't find you. So we're going to come back to you. All right, so we're going to be asking somebody to figure out what this angle is, which is the cosine to the minus 1 over of 10 over 5 root 5. Christopher, it's your turn. Could you check in for me, Christopher, first of all? Let me know that you're there. Christopher. Great. And Shashti, I'm still looking out for you. I'm still asking for you. Are you there, Shashti? Still not there. Okay, Christopher, could you work that out for us, please? Tell us what that angle is. 26.6, he says. By the way, please make sure you're back in degrees now. I know we had to switch over to radians a few minutes ago, but please make sure you're back in degrees now. You're working this out in degrees, Christopher? You are, okay. And everybody else agrees with Christopher's number? Yeah, okay, great, Carly. Thank you, Tamalia. Thank you, Jordan. Okay, great, fantastic, fantastic. So what we're saying is that these two, vectors, right? One that's 2 minus 1, I guess, is in the third quadrant. Sorry, the fourth quadrant. And 3 minus 4, I'm going to see that would be in, oh, they're both in the same quadrant. The angle between them is 26.6 degrees. Now we can easily find the angle between two vectors by using this. Well, it works out in 3 space as well, right? We're going to go through the same calculation, but for 3 space. So I'm going to be calling on one of you. So now we're going to be working on this vector, these two vectors, sorry. But we're going to apply the same principle, right? We're going to say that the cosine of theta is equal to the dot product of those two vectors. So 2, 5 minus 1 and 17 minus 7 minus 1. Let me go back to my wheel. Christopher, I'll take you out for now. Shashti, I'd love to hear from you, right? I think it's now time for you to step up. So Shashti, are you now there? Still not there. Okay, so I'm going to go to Tomaleo on this one. Tomaleo, could you check in for me, please? All right, perfect. Can you give us the dot product for this is the green line now we're talking about. Can you give me the dot product for the u and the v vector, please? All right, what is that dot product? We've done this a few times now, so I think you know how this works. Ooh, 0. Okay. Okay, so getting 0 on top. Now, and you're getting, Kush is getting the same thing as well. Do we need to go any further with this? Or do we already have the answer to this? Should we go any further? Because Sarah says no. Why is Sarah saying that? I don't just mean Sarah. And Ariana says no, we don't need to go any further. Why do we just sort of draw a conclusion right now? And what conclusion are we drawing about these two vectors right now? What do we know about these two vectors right now? The angle will be 90 degrees, right? They are orthogonal vectors, right? They are right angles to each other, is what we're saying. And the truth is that, remember that it doesn't matter what I put at the bottom here. Whatever these magnitudes are, they could be 10, they could be 500, they could be anything. 0 divided by anything is still 0. You're not trying to divide by 0. That's undefined. 0 divided by any number is still 0. So therefore, I'm going to be asking you to find the cosine to the minus 1 of 0, which is in fact 90 degrees. Okay, so once you are working this out, and we could have gone further, we could find the magnitude of these two vectors, if we wanted to spend more time on this. But the fact is that once we find that the dot product is 0, end of story. The dot product being 0 already tells us that these two vectors are perpendicular. So the angle between these two vectors is 90 degrees. Okay, now let's try this one. All right. This triangle has vertices, and they give us the vertices of the triangle, A, B, and C. And this is a triangle in 3 space, right? They want to know the angle ABC. So going from A to B to C, in fact, it's the one that's marked. What is the size of that angle? Now be very careful, because for us to be able to find that angle, we need two vectors. I'm going to say this very hopefully clearly so that everybody knows exactly what we need to do. We need to find the two vectors that meet at B. Okay? Let me say that again. I need to find, if I want to find the angle between two vectors, A, B, and C, the vector, the one at B, the angle between two vectors when they're tail to tail. So look at what Adam just said. I need to find the BC vector and you said the AB vector. No. Okay, so you're right in one case, but not right in the other. The BA vector is what Kushi just said, and that's what that's what we need to do. Absolutely, Kushi, right? We need to find the BC vector and the BA vector because those vectors are tail to tail. Think about the first letter that we start off with. The first letter is the B. So B to A and B to C are two vectors that are tail to tail. Okay, so first things first, what is the BC vector? What are the components of the BC vector? That's what we need to figure out. Now, does anybody remember how we do that? We have done this before. Remember, I'm going from B to C. Remember that. That's important. Look at Kushi. Look at you. Look at Richard. Look at you. Excellent. Excellent. It's head minus tail. Okay? So the head of the vector is at C. The tail of the vector is at B. So we're going to take the C vector and subtract the B vector from it. So I'm going to ask one of you for those. Don't put anything in the chat yet, please. Let me take out Tamalea. Tamalea, good job. My wheel getting very slim now. I've taken out a couple of people already, but we still have a lot more to go, including Shashti, by the way, who hasn't shown up for today's class, really. Ashvan, your time. Ashvan, show up for me, please. Let me hear from you. Let me know you're there, Ashvan. Usually you're quite attentive, so let me hear from you. Where are you? Ashvan, perfect. Okay. Shashti still looking for you. Are you there with us now? No. Okay. So, Ashvan, can you tell us what the components of the BC vector are, please? What's my X, Y, and Z component? And remember, you've been told that it's head minus tail. So give me that BC vector, please. The B to C vector. So give me all the components of that vector, please. The X, the Y, and the Z. So I'm hearing -1. Oh, -1. I'm hearing 6. And I'm hearing -2. Okay, let's just check in with the rest of the room on that. Is Ashvan onto something here, folks? Not on something. That would mean something completely different. Oh, he has -6 as well. Is that -6? Yeah, that looks like -6. So is Ashvan right about that? Let me check in with the rest of you. Did you all get -1, -6, and -2 for the BC vector? Okay, Vanessa and Richard and Taj are all in your corner on that one. Actually, let me do a quick shout out here because I'm hearing a lot from the same people. Let's see, where is Thomas on that? Thomas, what do you say to that? Does that sound about right to you? What you just saw there? How do you do? Okay, Ariana, good. So I'm happy to hear the question. You take the components and subtract them, but in the right order. As you heard earlier on, is head minus tail. The head of the vector is at C. So take each of these components that I'm pointing to now and subtract the B component. So 3 minus 4, then -6 minus 0, then -4 minus 2. Okay? All right. So there's my BC vector. And I also said I need to get my BA vector as well. All right, nobody put anything in the chat right now, please. So I'm going to come across here and take out Ashvan and see if I can get some help from the next person. And that next person is Ella. Ella, please check in for me, Ella. Let me know you're there. Good. Ella, can you give us the BA components, please? The B to A components. Remember, it's the order does matter. You're going from B to A, and it's head minus tail. So -2, 3, and 3 is what I'm hearing. And let's see what the rest of your classmates say to that. Carly and Sarah and Taj and Kushi are all in your corner on that one. All right, I'm not even going to check it for myself. I'm just going to go with that. Okay, so we have the two vectors, tail to tail, B to A, and B to C. And the angle in between that is, of course, the B angle. So I'm going to set this up for you now. The cosine of theta, right? This is theta right here, is going to be equal to the dot product, the BC vector, times the BA vector, dot product, over the magnitude of the BC vector times the magnitude of the BA vector. Okay, that's the procedure. The cosine of theta is equal to that. All right, thank you, Thomas, by the way, for chiming in on that. So, first things first, we need to find the dot product between the BC and the BA vector. And that task, thank you, Ella, I'm taking you out now. And that task is going to go to Brendan. Brendan, first of all, check in for me, please. Let me know you're there. Perfect. Brendan, give us the dot product, please. We got the BC and the BA vector. What would the dot product of those two vectors be? We're going to put that on top. Okay, Brendan, let me take you back to what we did when we did this before. When I asked you to find the dot product of these two vectors, you take the 2 times the 17, the 5 times the -7, the minus 1 times the minus 1, and you just add those numbers together. Okay, Brendan, does that help you out? Okay. Let me go back now to the one that you're working on. The BC vector is this one that we got on top, minus 1, minus 6, minus 2. The BA vector is minus 2, 3, and 3. I'm looking for the dot product of those two vectors. Brendan says minus 22. And do we all jump on the Brendan train, or does Brendan need to recalculate? What do you say to that, folks? Minus 22 sounds good to you? I'm waiting on the verdict. It's over to the jury at this point. Nobody seems to be agreeing with Brendan on this one. So is Brendan wrong? Did he make a mistake on this? Or have people forgotten how to do it? Jumping on the train. Right, Taj says yes. I did something wrong. I need a second. So Adam didn't get the same thing. But maybe Adam is the one who's right. I don't know. Taj says he's on that same train. Richard says he's right. Where's everybody else? You got no one's okay, all right, okay. With Taj and Ra, gotcha. Okay, minus 22 sounds about right. Right away, that tells you, by the way, that the dot product, I'm just going to remind you of this, you said this on the very first page, that when the dot product is negative, it does mean that the angle is an obtuse angle, which does seem to be, by the way. So that kind of makes sense. And now we're going to get some magnitudes. All right, so I'm going to go back to the room again. Let me remove Brendan for now. I need the magnitude of the BC vector and the magnitude of the BA vector. And the first one goes to Stephen. So Stephen, first of all, check in for me. Let me know you're there. Looking for Stephen. Stephen, check in, please. Looking for Stephen. Stephen, check in, please. Where is Stephen? Need to hear from Stephen. Where are you, Stephen? So that's both Shashti and Stephen at this point. Where is Stephen? All right. Give me one quick second here. Okay. Has Shashti since joined us? Is Shashti now with us? Shashti, are you there? All right. Definitely not good enough. All right. So we're going to come back to both of those people. I'm looking for a magnitude here, by the way. Just remind me what I'm looking for. Let's see. Vanessa. Vanessa. Are you there, Vanessa? Okay, so Shashti is now back with us. Okay, Vanessa, hang on for me, please. Hang on. We're going to come to you in a minute. Shashti, we're calling for you yet again. I need you to tell me what the magnitude of the BC vector is, please. All right, so the vector BC. We've done that a couple of times before, so hopefully you know what to do. But if you don't, let me know and we can walk you through it. There's a BC vector right there. I need to know. So Vanessa, just hold for me, please, for a little bit. Let me know what the magnitude of that vector is, because those two lines around it mean I'm looking for the magnitude. Can you tell me what that is, or do you need some help with that? Find the magnitude of the vector, the BC vector. Okay. Actually, Vanessa, in the meantime, could you work out the don't put it in the chat yet though. Could you work out the BA vector for us while okay, as Shashti has now come back with the root of 40, you're saying. All right, is everybody going to agree with Shashti on the root of 40? You got the root of 40 as well, Shira says. So Vanessa, in the meantime, could you work that out for me? So Sarah and Shashti are on the same train on that. So everybody else agrees with that, the root of 40? Or is there a different answer? What do you say, folks? Do I just write that down? Sarah says yes, and Adam says yes, and whoa, there's some disagreement now. Some people are saying 41. Got 41 as well. I know you all mean the square root, by the way. I do know that. but there's some disagreement. So who is right, who is wrong on this one? Let me check back with Shashti. Shashti, is your answer going to change or are you going to stick with what you got? Oh, it is a root of 41. Okay, all right, all right. Times, all right. Excuse me. So earlier I was going to call on Vanessa. Vanessa, do you have the other? And I agree with the short of 41, by the way. Vanessa, root 22. Okay, is everybody comfortable with root 22? Taj says yes. What about everybody else? Carly says yes. I don't see anybody coming with a different number. So I'm going to say the root of 22. Not 22, the root of 22. Okay, that's good. So you know where I'm going with this. Cosine of theta is equal to that. So theta is equal to the cosine to the minus 1 of all of this, minus 22. Now, generally, you can multiply the two square roots together. It could be the square root of 41 times 22. When you take the square root of two things and you take the product, it's the same thing as taking the square root of the product itself. Right? I didn't check that 22, but I saw quite a few people saying root of 22 and nobody objected to it. So I'm going to assume that it is in fact right. Okay, so that's 8, that's 8 and 4, 20. Yeah, it is 22. Okay. So I'm going to be calling on Stephen. Are you there with us now? Looking for Stephen. Taking out Vanessa. And I need to hear now from Thomas. Thomas, check in for me, please. Let me know you're there, first of all. And we're going to be asking you to do a calculation shortly. So I'm asking for the inverse cosine of minus 22 over the square root of 41 times 22, whatever that is. Or you want to take them separately, that's fine. Square root of 41 times square root of 22, doesn't matter. It's up to you. Tell us what that angle is, please. Give it to me to, I don't know, one decimal place. 137.1, Thomas says. Well, what do the rest of you think? Agreed. Agreed. Yes, same. That's what I got. Okay, I'm going to go with that then. There you go, folks. And by the way, I worked it out for myself on that one. I pulled my calculator out. And I believe that's what I wanted to go through with that. Let's right here. And I want you to tell me, because you're going to have this question in a couple of days. How would you even start to put this together? Right? There's one team pulling west, team A, pulling with a force of 500 newtons. There are two other teams, B and C. They're joining forces, but they're pulling one northeast, one southeast, and they're pulling with forces of 275 and 300. Now, adding those together, 300 plus 275 is more than 500. So on the face of it, it would seem that these guys should win over here, if you think about it, right? You're adding a 500 force, sorry, you're adding a 300 force with a 275 force. No, let me say this, if they were pulling in the same line, this would be a no contest. Because adding 500 and 275, sorry, keep saying 500, adding 300 and 275 together, if they're pulling in the same line, that's going to be, the sum of those is just simply 575, and that beats the 500 force going the opposite direction. So if they're both pulling east, no contest. The guy in the west gets pulled across the line, he loses, or they lose, is what I should say. But how do we tackle something like this? Do we have any ideas? Is there anything that we did maybe yesterday that might help us to figure out what the sum of all of this is? What force represents the final force of all of this? And which direction are we going in? Are we going to be pulling more to the west or pulling more to the east? That's really what I'm after here. Can anybody start me off in the 9 minutes that we have left? Can anybody start me off on how we would put this together? Come on, folks. I'd like to get some participation on this. I'm not calling anybody in particular. I'm just asking you how you would start putting this together, because you're going to have this question. right? So let's see if we can come up with a strategy right now, right? Any ideas? Make the chart like we did yesterday, Sarah says. I agree with you. So I'm assuming, Sarah, that you mean we need the x and y components of each of these forces. So that's what I'm going to assume, right? So and let me just take you back to what that looked like on the previous page, right? Well, we put Caleb and William and Kristen there, but we will use the team A, team B, team C this time, right? So let's say team A. Let's say team B. And let's say team C. Okay? So can you help me now to figure out, using team A, right? Remember that this is strictly going to the left. Strictly going to the left with and also think about this in terms of the coordinates that you would use to put in the X and Y column, right? Can anybody give me what team A's coordinates are going to be? Right? What would the coordinates be for team A? I want you to think about that now. Think about how we did this yesterday, right? Think about where the tip is of the team A vector, right? Where I'm pointing to right now. What would the coordinates of that tip be? Minus 500, 0, Sarah says. How do other people think about that? I'm not going to weigh in it yet. I want to hear what other people think. Does that make sense? Ashwan is agreeing basically with Sarah. But is that what everybody else is saying? Right? Is Sarah or are Sarah and Ashwan both right? Does minus 500, 0 make sense? So we don't even need to use sine or cosine or anything. That we can just write that down as being the coordinates. What do other people think? Can we go back to the question? I sure can, Ariana. Right? These red lines represent the vectors that are for the forces. So team A is pulling 500 newtons west. So this red line that I'm pointing to here represents team A, pulling 500 newtons west. I can put the 500 on it, right? So 500 N is team A. Team B, and by the way, let's just stop there and just ask the question. Does the the information I just got from Sarah, and Ashwin agrees with that, does that square with the coordinates that you'd expect the tip of this vector to be at? Minus 500 and 0. Think about it as being x and y coordinates, right? Does minus 500, 0 sound about right to you? That's my question for the class. And I haven't got any answers apart from Ashwin and Sarah. Okay, Taj is saying yes as well. So we've got 3 people on. Okay, good. All right, so let's go ahead and put that in. So minus 500 and 0. No, we didn't use sine or cosine or anything because we're sitting right on the x-axis. All right, so it's pretty easy to come up with the coordinates without having to do anything else. Minus 500 and 0 makes sense. Y along the x. So I haven't moved along the y-axis, and I'm 500 on the x-axis on the left-hand side. Let's get to team B now. Team B is this vector right here, right? I want you to think of the x component. And by the, let me just remind you of something. This says north 75 east. I'm going to remind you what that means. It means I'm 75 degrees east of north. So this is north right here. 75 degrees east of north means this is 75 right here. That's what it means. Right? You're 75 degrees away from north going in an easterly direction. So what angle should I be using for team B? And remember, I'm going to remind you now that for x, it's cosine, right? So x is cosine. I start you off by saying that the magnitude of team B is given to be 275. So it's going to be 275 times something. What's that thing? Okay, so it's the cosine of the 90 minus 75. In other words, the cosine of 15 degrees. Okay? Is everybody clear on that? Does what Richard just said make sense? Because if it's not, we can go over it. Okay, good. I'm getting a lot of yeses there. So let's keep going. So if that is obvious to you, then it does mean that the next part should be obvious as well. This is going to be 275, not cosine anymore, but the sine of 15 for the y component of that. Now here comes a more challenging one. Excuse me. Team C, and I don't know why I spelled team with an N. Okay. Team C now. Now let me remind you what that coordinate is, or that position is. This says south 85 east. South 85 east means I'm 85 degrees east of south. That's 85 degrees right there. Right? Now, the challenge is, and I know we have to finish up soon. The challenge is, and I'm going to put this the length of the vector there to start you off. This vector is 300. Is to figure out what angle is going to make sense for us. Does anybody think they know what that angle is? 270 plus 85, Sarah says. Absolutely 100% correct. Which is how much, by the way? 270 plus 355. Oh, hold on. Something is wrong with that. Something is wrong with that because this is supposed to be just 5 degrees, 365. Yeah, why am I getting 3? It's 275. It's not 270 plus 80. Okay, yeah. So we'll put that in 355. Yeah, 5 degrees short of 360. Absolutely right. 355. For some reason, I was thinking 365. That's the number of days in the year. That's not what this is. 360 is a full revolution. So it's 5 degrees short of that. And you, I'm going to bid you all goodbye now. You can actually finish this question on your own because you can get that magnitude. And then the last part of this is to figure out tan to the minus 1 of whatever the y is over the x. And what does that mean in terms of what direction you're moving in? I'm not going to finish this question. I'm going to say you should finish this question on your own, right? If you want to just leave it there until you see it again on the test, that's up to you. But the question is, what's the magnitude of the final when you put this all together? And secondly, who's winning this competition? Is it going to go to the west or is it going to go to the east? It may not go in a straight line west or straight line east, but is it tending towards the right side or tending towards the left side? On that note, 12:36, I took a minute of your time. Have a great lunch.